Welcome everybody to this second day of the second week of the school and the second lecture by Antonio De Rosa. So, please.
Thank you, Giovanni, and thank you all for joining in this festivity day. So I appreciate your effort in skipping the festivity. I think that today is city holiday. Yeah. Okay. So where we were left yesterday. So remember, I showed we computed together this monotonicity formula for local area minimized and some variables. Yesterday. And we show that for sigma D, that is local area minimizing, then we show that the derivative R of R over R power D bigger or equal than 0, where f of R is the d-dimensional area of your surface sigma in the ball of ellipse. Okay, so this is an interesting property because it allows us to do structural analysis now that we state the extension of these to stationary variables. This is an interesting property because it allows structural analysis, local analysis of your candidate with stationary surfaces. Because essentially what you can do thanks to this formula is that this is sigma is your surface. Now here it's moved, so it's less relevant what I'm saying, but essentially what you can do, you can pick a point P on P. You can pick a point P at this surface and you can start rescaling this around this point. Okay, you can look closer and closer at this point. And we will see in a second that in the sense of measure, we will be able to pass to the limit because this rescaling specifies some monotonicity formula on the mass. So in a sense, you have a uniform amount on the mass of this object as you keep increasing. If you fix this guy to the ball of radius 1, centered at 0, same notation B01. In this guy, there will be a uniform bound on the mass, and so you can pass to the limit in the sense of measure. So this is why we care of extending these to stationary variables. And actually, the proof is more or less the one that I gave for local area minimizing. The difference is that since you are not allowed to use competitors for stationary variables, you have to take a vector field that mimic the cone competitor. Okay, so this is kind of an exercise for you where I do some hints. Exercise. If you have a stationary variable, there is an equivalent formula for variable with the locally bounded first variation that involves adding an exponential to the formula, but let's keep the computation for the exercise simple. So let's just do it for stationary variables. If you have a stationary variable, what I suggest you to do as a hint to extend this monotonicity formula for stationary variables is to consider the characteristic function of Brx, same notation, and to approximate these approximate it with something smooth. So for instance, something of the following type, phi j of say x minus p. You want to rescale by the radius so that you bring the function phi j in the domain at scale 1. Okay. So, and you want to image phi j something like this. This one. Want phi j to be something like this. Okay. Phi j. And the j is this. J, now I say in a second.
No, they are in the picture. There is no J.
Oh, J is, this is a sequence of functions. This is converging to the characteristic. Oh, okay, I understand. Yeah, thank you. I understand the question. So indeed, what I was about to say is that you want to take phi j, that is equal to 0, and the characteristic of the interval 0, 1. Okay. And I mean, it's just a bit long to do the computation, but it's very elementary. That if you plug, you take phi j that is converging to the characteristic of 0, 1, and you plug the vector field xj, that is this smoothing function phi j in x minus p over r, and you multiply by the radial vector field x minus p. Okay, so you just, there is not much to do. You just take this vector field, you plug it into the first variation. Essentially, what we are doing is that sorry for the wait. What we are doing is that we are replacing the home competitor with an infinitesimal deformation that is straightening up your variable in the direction of the cone. So infinitesimally, what you are doing is that this is your variable, you are kind of straightening up in this direction, in the direction of the cone with respect to the trace. Okay, so independently of what was the standard plane. And in the limit as j goes to infinity, so as j goes to plus infinity, the exercise for you to do this computation is to show that you recover that the mass of the varifold in the mode of radius, let's say, capital R x divided by omega p r d, r power d, is equal to the mass of your varifold in a smaller mode, scaled by the corresponding area of the d-dimensional disk. Okay? And this would be good if you remember the computation that we did last time for area minimized surfaces. Remember when we applied area formula, there was a factor coming from, there was area factor that was, if you remember, 1 over, remember there was a factor given by the integral of 1 over the projection, if you want, on the plane of x over normal x. Right? So this guy was reflecting the fact that you have an area factor that is strictly less than 1, the full fraction, if the surface is not cutting the sphere orthogonally. Okay? So in this case, for instance, it's not cutting orthogonally, and you expect that you have an inequality principle. And the closer you are to cut it tangentially, the worse it gets, right? Because you get the area factor that has to count a lot of this. And the same computation that we did yesterday, you will find it out via this procedure, because here it will pop out something like this, 1 over d, the integral of the Grassmannian bundle of the annulus, d capital R x times this all R x, of basically a comparable term. So you will get the gradient of S on S orthogonal So on the orthogonal space of the tangent plane x, okay, of the norm of x minus p, well, divided by x minus p power the dimension, this is integrated in dpxs. Okay, so this will account essentially for the same information. Probably here I just want to give it what it means. This the gradient S orthogonal of a function is simply the projection of S orthogonal of the gradient of the function. Okay, so this is the full gradient, and then you project it on S orthogonal. Well, S orthogonal is the orthogonal to the tangent plane coming from the Grassmannian part of your varifold. Of course, it doesn't need to be unique at this point. There may be multiple planes to take into account, at least for what we know up to now, but there is this component. Okay, so if here you have multiple tangent planes, in principle, you may need to take multiple projections. Okay, so this is kind of easy, it's just a bit lengthy as a computation, so it's a good idea not to do it.
This works for rectifiable, non-rectifiable.
Yes, this works for every varifold that is stationary. So it doesn't depend on the rectifiability. So we will deduce the rectifiability from assuming that the first variation is 0 plus the positive density, but here we are not requiring that the density is positive to make this computation. This works, yeah, for every varifold. And but from this information we will get in a, like today I think we will be able to prove the rectifiability theorem of Allard, but also it's good to remember this because let me give already a spoiler, but I think probably it's already very intuitive for everyone. So you see this guy, let me observe precisely that this quantity here is bigger or equal than 0, right? Because it's a square. In particular, this gives you the monotonicity of this quantity. So this gives you that the mass in the ball of radius little r, so the density ratio, sorry, is less or equal than in principle of the density ratio in the ball of radius capital R. Okay? But here, this inequality will be saturated when this guy is 0. Okay? So this will be saturated, this inequality is saturated when if you want this guy, gradient S orthogonal of norm of x minus p is equal to 0 for W, sorry, we are still at p, for b almost every x and s, right? So what does this mean? This means what is the gradient S orthogonal of this guy? The gradient of this guy is x minus p over the norm of x minus p, right? So what are we saying? We are saying that this guy should be 0. So in particular, x minus p must live in S, right? So x minus p is in S, p almost every. Okay, so you start seeing already this is not a formal proof that blow-ups are cones, but it's indicating that, right? So it's saying that every time you have your varifold, this is a ball of radius r, you are saying that at the point x, this is p, x minus p should be in the tangent plane at x, right? So the tangent plane you should imagine kind of this guy. If this is happening at every point x, you are imagining that this becomes a cone. This is not a proof, I will do the formal proof after, but this is just to start having an intuition of what's going on.
Sorry, so this saturated statement is not independent here.
No, no, yeah, I'm saying that if this inequality is saturated, then sorry, let's see. So seems that if it's independent, so okay, so if this is equal, then this is so what is significant is the conical property eventually. So what is true is that if this is equal to this integral has to be 0. So this is an independent leaf with this guy being always almost everywhere equal to 0. So up to here, this is an independent leaf. Sorry, I was a bit careful in this because we will see something that you can deduce from this that is not an independent, but this will come in a second. So up to here, it's an independent. Thank you very much. Of course, assuming the stationary. Okay, so we will see that on the other hand, there are some properties that comes out of these that are not an independent leaf, are just implications. So that this implies something. Okay. Pretty good. But before going into that, I first want to show some properties of the monotonicity formula. So the first property that I want to mention is what I was referring before. That is first corollary. Corollary 1. The density exists. The density always exists. And this is a simple, it's an obvious fact because remember that the density of the mass of your varifold at the point E is just the limit of this quantity that we have to the limit as r goes to 0 of the density ratio. Okay, so here there is not much to say. You have a monotone function and the density exists. The other interesting property that I want to mention is what I was referring to before when I was saying that we can do structural analysis, because, and it's the fact that blow-ups always exists. Now I say what the blow-up is. Ups exist. What do I mean by this? So if we look at eta P R, have I introduced already dilation map? I think so, right? Let me.
Someone did in some course.
I don't know if I introduced already the notation. Let's go for the whole course eta XR of, let me say, PR of X minus P divided by R. I don't know if I have introduced, but let's say, let's fix this notation throughout the course. Okay, this is always the direction map. What I wanted to say is that if you look at the mass of eta PR, push forward the varifolds, and you compute in the ball of radius capital R 0. Okay, this is what? This will be equal to the mass of the varifold B in the ball B R, but now you see you have done a rescaling by R, by little r. So this will be B capital R, little r. Okay? And if I were stopping here, there was a mistake. Remember, the reason why we are introducing varifold is that now there is the the Jacobian that kicks in, so it's not the push forward of measure, there is the Jacobian for any scaling is 1 over r power.
The name, the ERP.
Sorry?
ERP.
So if this was 1, this would be PRP.
I mean, I think it's zero.
So you have to, so let me draw a picture because this is already, I'm going backwards, right? So this is the varifold. This is the ball P capital R little r P. And this is the ball, oops. And this is the ball P R 0. So this guy is this guy. And now I'm going backward to the original varifolds. So R takes into account the fact that here we have capital R little r. And now, so the origin here is this, and here is P. And now you have to rescale by the Jacobian, that is R power P. Okay? So if we now take the limit as R goes to 0, little r goes to 0,
Either the by R should be, because I think that the scaling where the divides the
but no, but this is the difference between varifold and measure, right? That's what. That's the whole point of introducing. Yeah. So because let's remember what I was saying yesterday. So the whole point of why we are doing this varifold theory is that when you do the min-max, you need to prove that the limiting guy is stationary, right? So to prove that the limiting guy is stationary, I have to give a sensitive way to define the image that brings the Jacobian with it. And to do that, if I use just the theory of measures in space, then I will not carry this Jacobian. And so when I take the derivative in a diffeomorphism, I would always get 0 because the mass is preserved. But now, since I put the differential of S, restricted to S, I have to just. Yeah, thank you for the comment. Any other comment? Okay, so now if you take the limit as R goes to 0, okay, this guy is converging to the density that we know exists. Okay, this exists. So right-hand side converge to the density of the mass of the varifold. So in particular, you know that this guy has a measure which is locally bounded, uniformly locally bounded. So we use that eta P R push forward P is uniformly in R, little r, locally bounded. Right? Because I will always converge to the density and so be at 0. So since I'm uniformly locally bounded, then I can apply just Banach-Alaoglu, and so I deduce that the limit of eta P R push forward B as R goes to 0 exists some sequentially up to some sequence. Do we all agree with this? Okay, so it's just I'm just saying that the weak star ball is compact. So, yeah, the weak star ball is compact.
Why do you say locally?
Locally because
Locally now.
capital R, I had to set a big ball here in which to do the computation. Because in principle, my variable may be not finite.
You are assuming that the density is finite, the limit is finite.
This guy is finite, yes. But I'm fixing
Okay, so the variable can have infinite weight, but not finite.
exactly. So imagine, let's say, the very simple case, take a plane, HD restricted to a plane. Of course, I would be, here I would get always plus infinity. So I need always to restrict to a big ball, but the thing is that this is done for every R. So I fix R and then I do this argument for every R. And so in every compact set, I have a uniform R.
So the blow up will be a varifold on our end, not just on the ball.
Exactly, yeah. The blow up eventually is a variable dynamic. Because I do this for every R, for every capital R, and so I know that in every compact set, I am uniformly bound in the sequence in little R. So I can pass to the limit and get a variable in Rn that is.
So the variable means the nature
Is random actually, yeah. So the very, yeah, so you have the weight is a random measure, so well, as a very sort of yes.
I think there is a missing capital R of the D on the right side.
Oh, right, you are totally right, yes. Thank you.
Like,
Where is it?
there.
Yeah, there is it, it's there because, yeah, no, I understood. Let me fix it. Yeah, you are totally right. Let me fix it. So omega D R D, and here I divide by omega D R power D, and now this guy converges to density, and as is correctly saying here, I'm missing this guy. You're totally right, sorry, I was a bit sluggish.
Yes.
Because the density needs to be rescaled by the constant. Sorry about that. So,
Just have a question. So if your varifold is not, so let's say, is not rectifiable, more precisely, if your varifold, the density, I mean, is diffuse, like the one with the constant vector field in the plane. In that case, you get only trivialities, right? Because the density will be 0 and the blow up will be 0.
exactly, yeah.
Okay. And this also says that a variable cannot have density or cannot be too concentrated. Is that right?
So if you are concentrated, the density would be plus infinity. So in that case, yeah, you
Cannot be stationary.
exactly. We will see. I will anyways show this. If you want the reason why it cannot be stationary. Sorry, I always forget. To be quick, can I remove something from here that is not needed?
No.
No, I just want to give a very quick reason why, as what you're saying is correct. Because the stationarity, a very quick way to write it. So saying that stationary, a way to write it is that the integral of the divergence along the tangent plane is 0. So in a sense, you get the gradient of x, scalar product with s, against the mass of the varifold in x, and in d mu s, this is 0. Now, let me do a bit of just in the distributional sense. Let me do this.
And this mu depends on x, right? Is the
Let me do it already in the blowout, so that mu also doesn't depend on x. So we are looking at the blowout. Because yeah, for the blowout, you can say if you have an absolute point of absolute continuity for the Grassmannian measure map, you can say that this is constant in x. So this becomes gradient of x, the integral of s in the US, mass of the variable, and here you start seeing where is the trick, because now I will integrate my part distributionally. Integrate my part distributionally. is 0, you integrate by part distribution, and you get that x, let me call this guy A, let me use a bit distributional notation. You can fix these by test functions. And B is equal to 0. So what you deduce is that the gradient of B must be the kernel of A. Now, the kernel of A, these are orthogonal projections that are d-dimensional. So the integral of orthogonal projection has kernel that has dimension less than n minus d. So this guy, the dimension of the kernel of A is less or equal than n minus d, right? Because why is this true? Because the dimension of the kernel of S is n minus d, is equal to n minus d. And when you integrate orthogonal projection, in principle, you can kill some parts of the kernel. You just take the intersection if you want. And so this tells you something nice. This tells you, well, but then the gradient of B lives in an n minus d dimensional space. Lives in an n minus d dimensional space. Oh, pretty nice. Then I have at least d-dimensional lines. So I cannot concentrate because otherwise I would control this. Right? So this tells me I think, yeah, so I think it's instructive to see this in general, also to see the rectifiability theorem. So this tells you that in particular B, so what we are saying is that there exists this line, let's call it kernel of A. But then you have to have at least all these invariances. Kernel of A orthogonal. So along this guy, D is invariant. Is invariant. And this guy has dimension at least D. So you cannot concentrate more than, like, in a dimension that is less than.
It is for a block.
Yeah, I'm assuming to do this in the blow-up analysis, like take the blow-up in an absolute continuity point for the map that to X associate alpha X, or I was calling it mu X. Mu X, you take a point of absolute continuity, and then you would get that in the when you take the blow-up, this is constant in X.
Because you want this matrix A to be independent of X.
Exactly. That's but almost everywhere this will be. So this will be true. Yeah, that's a very good point. Thanks for the comment. That was very good to discuss. Any other question about this? Okay, pretty good. So we know that blow-ups exist.
General question. But this is a generalization of what people does with current.
I think that is yeah. So
because they are very full.
Yeah.
And
so you can forget, yeah, if you forget about orientation,
This is way more general algebra. Because you can prove that if you take the decomposability of the measure, you can prove that every blow-up is the tensor product of the decomposability bundle like tensor some other measure that is.
Yeah.
So the divergence free direction of the measures are always splitting. So this is a very general factor. It doesn't depend on it's just.
So let me say the interesting fact that is essentially also what Andrea is saying. The interesting thing of this proof, we will see probably in the last lecture, here, if you look carefully, you don't need to use monotonicity formula for this, because even if you forget about the monotonicity formula, which is basically the way we at the end proved rectifiability theorem also for integrals that are not the area. Even if you don't have the monotonicity formula, you will still, as Andrea is saying, you will still split the invariant space and the measure, the probability measure on the fiber, on this fiber. Then here it becomes a matter of density estimate. So you can say that the lower density, the positive lower density will say that you cannot diffuse much. And there is a bit more of harmonic analysis to do in our work to prove that the upper density cannot be too many times infinite. So then it becomes more an harmonic analysis. But this, I agree with Andrea, so this is telling you a bit more on the this is the thing, you just need to assume, we just need to assume that the lower density is positive, but we don't need to assume that the upper density is finite. This comes from, okay, this is not an easy theorem, it comes from this strong constancy theorem. It's a way to pass to the limit, these blowing up sequences, to pass to the limit is strong linear one, rather than just weakly in the sense of measure. And from there we recover a posteriori, no, not a posteriori, we recover in the middle of the proof that the density, the upper density is finite, almost everywhere, and then we can conclude with the other. Yeah, that's a very good discussion. That's summarized. It's good that we have a discussion because we summarize a bit all the.
This is the end of it, right?
yeah. Well, I don't know. It depends on you. I'm happy to discuss about this thing, so I'm excited about the topic.
What do you mean by the gradient?
Something? The gradient of that?
We have a gradient for that.
Yeah, so this is a matrix field.
Right.
A matrix field. Right? So it's a gradient of a vector field, so it becomes a field of matrices. Right? So every column or every row, depending on how you arrange things, as its gradient, it becomes.
No. Okay, the different. Okay, the usual.
Yeah, the usual. This is really the usual gradient. This is a vector field in Rn. You take the usual gradient. Yeah, I'm not using different notation.
Yeah. What do you mean by with the scalar product with
yeah, this is the inner product in the space of matrices. So it's
They're both matrices.
So these are both.
S is a matrix. If you see.
S is, okay, now I understand the question. You see, S is a plane. Okay, then, yeah, now I understand the question. S is a plane, I agree. S is in GT, but you can always see it as the projection matrix. I'm identifying S with the projection matrix. This is a matrix in Rn. And now I'm taking this matrix that is identifying the projection. I'm integrating these matrices in US, where here I'm using this little, as you are observing, this little identification between matrices and planes. This is now again a matrix, and I'm taking the inner product of these matrices. Yeah, that's a very good clarification. Yeah, I'm using this little identification. Thank you. Any more questions? Okay. Okay, pretty good. Where were we? Okay, so we proved that blow up exists. Now, let me start from, okay, let's keep this for a while. So a couple of small remarks that I want to do about blow up of stationary variables, because they will be interesting to understand the Allard regularity theory, like Allard C1 alpha regularity theory. Is that it's a couple of information about the blow-ups. So actually, well, the first one I give you as an exercise, and the second one we do it together. So the first is for you, fix, well, in both of them, fix a blow-up W of V at the point P, let's say. And V is as usual stationary. Okay, so you can show that as an exercise, very easy. Show that the density ratio of B in a ball of radius capital R centered at 0, omega D RD. Okay, so if you send, oh, sorry, this is the blow-up W. If you center yourself at the blow-up point at 0, then this will be constantly equal to R to the density, the d-dimensional density of the mass of the varifold P, which coincides in particular with the d-dimensional density of the blow-up at the origin. Why is this true? This is an exercise for you, but you can prove it using what I did before when I was fixing a big ball of radius capital R, and I was using a second radius to be scaled. Just use that idea and you will do this. So it's not a difficult. It's not a difficult exercise. So hint, use the same idea. As before. The license is empty. Because of course, of course, honestly, is what the one has done before, but
As good as I do it.
yeah, that's right. So yeah, it's not it's like I'm not. I can read it like. That's okay, but yes, exactly. That's but we didn't prove that yet. So we will eventually prove that W is a copy, but we don't know yet. So we haven't proved that W is invariant. Yeah. Yeah. Oh, okay, yeah, that's another good point. Well, but that's also related to another point. Notice that blow-ups are not unique in principle, they depend on the sequence, on the subsequence you choose to pass the limit. And actually, this is a big kind of open question. In the field, is not that there is not much known about this. If you have area minimizing objects, then in some specific case, you can prove uniqueness of the blow-up. You have, for instance, some good decays to the blow-up, you have a metric inequality. So you have to have really big example, a decay to the blow-up uniformly in the radius. But in general, it's a big question. In which cases you can prove the uniqueness of the blow-up? Just to say if someone gets interested in the topic, that's a big open question to understand the uniqueness of blow-ups. So the second exercise instead that we do together is show that for every x in Rn and for every r positive, let's call it capital R, so I distinguish it from the other one. The d-dimensional density of the weight of the blow-up at x is less or equal than the weight of the blow-up at any radius, centered at x, omega d RD, and this in turn is less or equal, so this guy in turn is less or equal than the d density of W at the points. So let's do this together. So first of all, this is still very familiar with the fact that you are considering a cone, because what is the interpretation of this density information? In a sense, we are saying the following. There is a cone that is stationary that probably you have already seen, or maybe not. So this is just a tripole junction. What we are saying essentially is that if you take the density at any other point, x here, you see here you have just one plane. But in a sense, in zero, if you are a bit singular, you start accumulating multiple planes. So in principle, you can expect that the density at zero is bigger. And in between, as you start zooming, you first see just this plane, and so up to, as you zoom, the density ratio is constant. At some point, you meet this guy and you bump with density ratio. Okay? Now, the proof is very simple because the first inequality here, A is monotonicity formula at X, end of the proof. Okay? And the second part, B, instead is nice to see at least once this argument, because this argument comes several times. So if you want to do the second part, you do the following. So let's say that you want to compute W of B capital R X over omega T R D. Okay, I want, so this is R. I want to take a ball now because I want to get the zero density. I want to take a ball that encodes also zero, that has center at zero. So what I can do is I can extend the radius by the norm of X and center it at zero. This is just less or equal, by second conclusion, then the mass of W in B R plus the norm of X at zero, divided by omega T R over D. Okay. And now I will not be sloppy as before, as your friend suggested. So I will remember to multiply by the right constant here. So capital R norm of X 0 divided by omega D times R plus norm of X power D. Then you multiply by this guy. And then you divide by R power D. And that's the end of the story, because this guy converges to density, and this guy converges to 1. Right?
Sorry, but R is not moving.
Sorry?
Converge when?
So,
as R goes to infinity.
yes.
But that inequality R is fixed.
But in R there is monotonicity.
Okay, good.
So it's,
Sorry.
it's enough to estimate huge balls. Huge balls control the small balls. Yeah, that's a yes.
Yeah, sorry.
That's a very good point. So R big control R small. So it's enough you control the limit and you control all the scale before by monotonicity. So let me say that this converges to theta D 0 and plus monotonicity formula. You complete. Okay, so this is an interesting property because it reflects more and more the fact that these guys are cones. So it looks we are going in the right direction. And with the same idea, I leave this as an exercise because it's really exactly this computation we did. You can prove something that is peculiar of stationary variable, that the density is upper semi-continuous when you take points, see a sequence of points that is converging. So you use exactly the same proof. So I leave this as also an exercise. Really the proof is the same as point B. And actually, this type of argument happens a lot of time. So, exercise. Exercise for you. If you have a stationary variable, then the density is upper semi-continuous. D is upper semi-continuous. Well, what does it mean? It just means that you take Pj converging to P, then the density at P of the varifold is bigger or equal than the limit soup, sorry, on J of the same density at P. The proof is again the same as I was saying. I would like just to discuss the fact that it's sharp. You cannot expect continuity in general because of the example that I keep giving you the same example. So if you take the triple junction, okay, so these points here at density 1, when you pass to the limit, here you have a point of density 2. So you can have a jump, a gap of upper semi-continuity, so you cannot expect continuity there. Sorry? Oh, sorry, real. Yes. Exactly. Yeah. Okay, so maybe a better, so because in principle I never showed you that this is stationary, but something that for sure you know that is stationary is that if you take these two lines, just because we saw that the first variation is a linear operator, so if you sum two stationary objects, it's a stationary object. So this plane is stationary, this plane is stationary, so you proved for yourself that this is stationary. These are points of multiplicity 1, and this is the point of multiplicity. So I just wanted to give you something that you already know that is stationary. Okay, pretty good. And actually, you can make this even stronger, in a sense. The strengthened information that you can get from this kind of argument is the following, that we will use it in the compactness for integral varifolds. So this is important to remember, and if you want, it's again an exercise for you. Is if you want a sort of upper semi-continuity for the support, let's say, assume that you have a sequence of varifolds that are stationary, and the density of these varifolds is always bigger or equal than 1 for every P in the support of J. Okay. And assume that Vj is converging to V and Pj is converging to P. Then you can deduce that for the limiting varifold, the same property is true. So you can prove that P is in the support of the mass of the varifold, and the density of your limiting varifold at P is bigger or equal than 1. Okay, so in a sense, it's a kind of upper semi-continuity for the support. So you cannot, from one side, you cannot lose on the Hausdorff distance, in a sense, right? So you are always limiting to points that are in the support. Okay, so now we go to the rectifiability theorem. And for the rectifiability theorem for varifolds, we will use a very basic rectifiability theorem for measure. There are a ton of experts in the audience about rectifiability theorem for measures. So here I'm using a very simple, I will use a very simple rectifiability theorem for measures. So even weaker than Nastran. So the rectifiability theorem for varifold, as I was anticipating yesterday, theorem of rectifiability, says that if you have a stationary varifold, and as we were saying yesterday, with what we were discussing about the rectifiability for stationary varifold, you have to assume also that the upper density of your varifold is positive for V almost heavy X, then B is rectified. Then B is rectified. Okay, and I already explained what rectifiability means. It just means that the weight is a rectifiable measure, and the Grassmannian part takes as Dirac delta on the tangent plane of this rectifiable measure. And we already saw the example that this is sharp. The density positive sharp. Think about again L2 on R2. And which is stationary. And, but as you see, I'm not assuming that the density is finite, as we were discussing like a minute ago. So in order to prove this, I will use this theorem for measures. We can discuss also the proof together. So this is theorem. If you have a positive random measure, well, there are generalizations, but let me state it in the form I need it. Positive random measure, mu is rectifiable. If and only if the lower density is positive and the upper density is finite, mu almost everywhere, x, and for almost and for mu almost every x, there exists this idea resembled the intuition we were discussing before, also with the comment from Andrea. So there exists a sort of a plane of invariance actually. In this case, it's much more rigid, the assumption. There exists S of x in the de-Grassmannian. In the de-Grassmannian such that any blow-up limit, any subsequential limit of the dilation measure of eta x r push forward mu, and here now I have to rescale by r power minus v because now I don't have the Jacobian, is CHD restricted to Sx, where C depends on Rj, on the sequence Rj. And C is a positive number that depends on Rj. Okay? So for the area functional, I just need this result because you will see that the monotonicity formula is powerful enough that will give me the same Sx as a blow-up limit for every sequential for every subsequential limit. But it's good that we had the discussion before because actually this result can be strengthened. But this is I think significantly, it's more difficult to prove, and this is due to mass standard. And I tell you now what I mean by that. So, I mean by this is that the mark theorem holds also if Sx depends on the subsequence. But this is a more result. I'm not going to discuss this. This is used. Okay. This is a remark, but for us, we suffice this rectifiability theorem function. So I don't know if you have already seen the proof of this kind of result. Otherwise, we can get it together. Okay, so okay, then we can show it together. Okay, so let's first do this theorem. Good. So I will just sketch the proof of the implication that I need actually, the difficult one essentially. That is, this is see, this is trivial. This is trivial. So we just need to discuss this image. Okay, so.
Isn't the choice the constant part of the Wednesday restrictive? I remember that I used like any if there are constants such that is then standard.
So I think
Okay.
I think that is
Okay. No, it's okay.
because once you know that, so
The
you
constant that is
so the thing is that if you are in that regime, take a different constant, you get always either 0 plus.
okay, yeah, it's fine.
Okay, so okay, so first of all, we can show that mu. Something that is easier to show is that mu is equal to f times hb restricted to kappa, where kappa is kappa is for L and hd sigma finite. So this is an application of Vitali. This can be proved plain. Plain. So the proof of the claim is an application of Vitali.
Sorry, what is F here?
Sorry?
What is F here?
Oh, there exists an F such that.
Oh.
So I'm just claiming I can write mu. Basically, I'm just saying mu is absolutely continuous with respect to such a function. So this is the first claim I want to show. So F will be just one second. So the proof will be mu is absolutely continuous with respect to this guy, and then F will be just the derivative. And why this is true? This is basically Vitali. So also Vitali covering theorem, lemma, Vitali covering lemma. Well, let's see. Vitali covering lemma. So it's Vitali covering lemma tells you that if you have given the sequence P Rj Xj of a family I, not necessarily countable, so generic family, and sup of Rj J is finite. Then there exists a subcollection J infinite, such that the family B Rj Xj is pairwise disjoint. pairwise disjoint. Is pairwise disjoint, and you can include the union of all these balls just in the union of these fewer balls. If you expand them by 5, if you rescale them by 5. 5 is not sharp, probably you can do 3, I think. Well, I don't know what is that. You should go through the proof. You can go through the proof, and I think you can get even better than 5. I think for sure you can do 3 or something. So, yeah, sorry?
Not one.
Not one for sure. There is something that is, but 5 is clearly not sharp. So, but anyway, let me write it in this way. That is the union J of BRJ XJ is contained in the union of J in capital J in the subfamily of B5 of J. Okay, I'm not gonna go through the proof of this, so it's it's an easy proof, you can just check it out. Okay, how do we prove that characterization essentially of the dimensions that are absolutely continuous with respect to HD? It's just an application of Vitali by defining correctly K. So as you can imagine, I don't have many choices for K. My assumption is this one, so I can just take K to be the set of points where, for instance, the upper density is between 0 and plus infinity. So, on the plane. Of plane. Take K to be exactly set of point X such that the upper density is positive and finite. Okay. Let me do sketch. I think it's something complete beyond the proof. Sketch of the proof. So you take this. So first of all, we can do this proof by assuming we assume that mu of K, mu over mu is finite. Can show that you don't need to do plus to make this assumption. Check as exercise case. Okay, then you can actually, so you want to use this information, but you want to use it in a slightly better way. So you can approximate this. K with a slightly more uniform lower bound on the upper density. So you define KT to be set of point X in K, such that actually the upper density is with respect to mu of X is bigger than T. And now by Vitali, you can make estimate on this KT. Okay, so by Vitali, you can estimate mu of KT with what? With 5 power T divided by T HT of KT. So the hint for this is just coming really from the definitions. If the upper density is bigger than T, for every point, there is a radius for which this is, the density ratio is bigger than T. And this will be your initial family I of balls. you start but then you apply the Vitali covering lemma to restrict to something smaller, which is disjoint, so that you can recover in some the measure. And then you use the fact that the radius is 5 to bring it up, because now you are looking at HD. So you know how HD scales, and you bring this out, 5 power d. And the 1 over t here will appear just because you are comparing the measure mu with respect to the HD measure. Okay? So this is the hint to do this. So prove this as an exercise. But the hint is pretty clear. As exercise. And in particular, this is telling you that if you take the union in T, if you take the union in T, it's equal to the union of K1 over N, or N in N. So this means that K is HD sigma packet. Okay? And now, as an exercise, it's kind of the same argument. You don't even need to use the tally. Try as an exercise. This is super easy. Try as an exercise that actually mu is absolutely continuous with respect to HDS. Okay? And so you can take the derivative of mu with respect to the HDS to K and you go. Okay?
I would expect like one of the training qualities to be the opposite side of the side, like, or something like that, because we have like then.
Oh, yes, you're right. Sorry. You're right. So. Potential here. Go back anyway. I'm assuming. Sorry. Okay, so now let's use this result to keep going and showing the rectifiability of the measure. I don't know how much time I have left. 10 minutes, okay.
We start.
Okay, but I think I can do the. Okay, so let's prove now that this guy is rectifiable. So we remember where we are, so I can do this. Right. Okay, so the variability proof. So we want to show to prove K is rectifiable. In order to do this, let's do the following. If you fix a delta positive, and you fix a plane S0 in the Grassmannian, and the lambda positive, I can consider the set K prime, which is a subset of K, a bit better behaved, so the set of the point X in K, such that I put some lower and upper bounds on the lower and upper density. lambda minus 1 over density. Let me abbreviate, anyway, we know what we are talking about. Lambda, so instead of 0 plus infinity, I have 1 over lambda lambda. And also remember the plane of kind of on invariance, so that supports the limiting blowups, rather than being just a generic XX, is delta parallel to S0. S of X minus S0 less or equal than delta. Okay, so you are delta parallel to S0. If you want to take the metric that I can use is just take the projection operator and the distance of the
distance of the.
so this is
the angle is small.
the angle is low, yes. They are delta parallel. Yeah. So they are kind of
Those parallel things.
sorry. So yeah, this is basically saying that this angle is that comparable to that. You're right. Sorry about that. Okay, so first thing, we agree that I just need to prove the rectifiability of K prime, right? Because K can be written as a control union of this type of set. Because I can just take lambda equal to n and take the union over n, and I can make a finite cover of the Grassmannian, and the Grassmannian is compact, so I don't have issues. So this is K prime. So this has to be proved to be rectifiable. Even better than that, you can do a second approximation. You can fix a row so you can fix row and consider the subset K second of X in K prime such that you have flatness even in the sense of the rescaled measures, in the meaning that if you take the weak star distance of eta x r forward mu. Let me restrict it to all over H1 divided by mu xr. I just do this so that I'm sure it's a probability measure, so I'm not getting that distance given just by the fact that I'm not rescaling correctly. With HD restricted to Sx intersecting P1, 0 over omega t. This distance is less or equal than delta for every r less or equal than rho. Okay. Again, little exercise for you. You just need to prove that K second is rectifiable. This is just by compactness. By compactness, exercise for you. Show is enough to prove K second is rectifiable. Okay. Now, since K second is rectifiable, it's easy peasy, I do it for you. So why is K second rectifiable? Yes, because I know. Notice that I rescaled. This is why I rescaled by mu bxr. So the C, if you want, is disappearing in the fact that I'm rescaling on the left, on the measure on the left by mu bxr. So I'm already, the left-hand side is always a probability measure. So I know that the constant there should be 1. So this is a typical trick in particular this is typical, the same as taking price blow up. When you take a price blow up, you rescale by the mass of the measure, so that even if you don't have density bounds, you always know that you can take the limit. In this case, I'm just doing it to get rid of the C. Yeah, so in order not to take care of the C. Yes, thank you for the question.
Like distance in the variation distance.
This is the weak star. This is the weak star topology, the weak star metric. Because we know that in the weak star sense, we are assuming that all the blow up limits are converging to HD restricted to Sx up to a constant. So we know by compactness that this should be true.
And it's not ultimatizable probability.
In probability measure, yeah, because these are probability measures.
So like
Exactly. Yeah. Okay, so let me prove just this last thing, and then lunch. Proof that K-second is rectifiable. Take 2 points, X and X prime in this set K-second. Okay, so we are at a given fixed scale rho. So say that X minus X prime is less than rho divided by 2. And let's call this distance actually R divided by 2. So R will be for the 2 times X minus X prime. This is R. Okay. So this is X, and this is X prime. I take the dilation beta XR of X prime. This push this dilation the following. This is 0. And this is Y prime. Now this guy will be always of length 1. What I want to show is that, in a sense, since this is now fixed constant equal to 1/2, I want to show that this Y prime is delta close to Sx. Because if I show that it's delta close to Sx, and Sx is delta close to S0, I will show that basically all couple of points are delta parallel to S0, and then it's an easy exercise to show that this is contained in the. Okay, this is the moral idea. So how do I show this? Well, this is where we remind that, we call that eta XR push forward mu in a ball BSY. So the only way to show that this guy is delta close to Sx is by using the geometric information that I have. So to take a ball here around this point, Sy, and see how much mass there is in this ball. Okay, so I take this guy, I rescale it by mu XR. Okay, and I know that this guy is mu d. This is SR X prime divided by mu Rx. Now, you can check as an exercise that by the density assumption, you can assume that this is something that depends on lambda, S power D, say S 0.1/4. But what I know is that this guy, on the other hand, by the way I define k second is delta close to HD restricted to Sx, right? So I know that up to a delta, up to the delta, I also know that that guy, HD of Sx intersected P10 divided by omega B is C lambda S power D. Okay? But I knew that also Sx, so what I discovered is that Sx should be here, right? Because in this ball I should see enough of the plane Sx. But now I remember that Sx is delta parallel to S0. Right? So in particular, Sx is delta parallel to S0. So what do we deduce? We deduce that y prime is delta parallel to S0, right? Because we just showed that this guy here is delta. This is constantly 1/2. So the ratio is something comparable to delta. So this is the A intersection by Taylor expansion. This is the delta parallel to S0. And now you conclude the proof with the following exercise. How do you conclude the proof from this? Is that if you take, if for every x prime couples that are in k times k, x minus x prime divided by the norm of x minus x prime is delta parallel to S0. I don't have enough space. It's a bit annoying that I have to. Can I continue here? Because it's the last sentence, so otherwise you wait half an hour just to see the three words. Is delta parallel to S0, then K is contained in the graph of a Lipschitz function, F Lipschitz. This is very kind of easy to prove because you are saying that at every scale, whatever is the point that you take, the two couples of points, the couple of points that you take in your K, their inclination should be always comparable to that. Right? So you cannot make the Lipschitz constant explode, and all your points you can interpolate them in a Lipschitz graph. And so actually not only is rectifiable, actually is just containing one single Lipschitz graph. And I think I should stop here because again I stole you 5 minutes. Thank you for the attention. Okay. Are there questions? More questions from you?
Is there like a hidden use of physical theorem? Because we are like, maybe not, because we need to, I mean, we are restrict ourselves to k second, and we use mu as if we have k, or no, maybe not.
No. So here you really don't need to do much about covering. So the covering at Vitali, I just need it there, but it's the usual place where you use Vitali, where you really want to sum up balls and you have to use that they are disjoint. So.
No, it's just because usually I remember that at least we need to, if we want to say something about a point in this reduced set, this smaller set, we need to use a point that is not a density point for the complementary inventories. Maybe not.
No, I don't think that here you need here you just restrict it to this lower set just because then you can just take the union of all these Lipschitz graphs that you get. I don't think that you need any. Yeah, I don't think that you need any reciprocate shears. Yeah, because one thing that I don't know if it was clear, but then basically the idea is that to go up reverse machinery, then you have to take all these Lipschitz map, each of these over k second, and then you take all these countable units over the original rectifier. So this was the last thing that maybe I didn't say, but you don't need any other type.
So I guess the application to stationary varifold we will see.
In the third lecture, I will. So tomorrow I will prove the rectifiability of varifolds and the compactness, and I will.
Thank you again.
Okay, so at the end of the last lecture, one of the students here asked a question which I didn't understand. But then I went home, I thought I did understand what he was asking. And it is an interesting question, so I'm not worried about him because he's a very good student, so I'm sure he knows the answer by now. But it's probably something I should explain to everybody. So I had this circle example yesterday. So let me just call what the argument was. So you have a circle, a point, and an angle theta. And they use C as an oracle. So the exact definition doesn't matter. The question is how you use something as an oracle. And really what you should think of is that you know everything about the circle, and then you ask what. Now how difficult it is to define things. How difficult it is to find the point x if I already know what the circle is. So if I want to find the point x, so I want to find the dyadic cube containing x, and I know what the circle is, this is not more difficult than finding the angle. So if you know the circle and you know the angle, there is an easy computation which tells you what x is. And since this theta is a real number, and we had a fact before that in RD everything has dimension between 0 and d, and so this is bounded by, dimension is now 1, so it's like bounded by n plus a constant. Every number of length n can be found in n steps. You can just list all its bits. And now I divide everything by n, and I take limit, then the dimension of x given so how difficult it is to find x if we already know c, this is bounded by 1. And this somehow corresponded to the fact that c is one-dimensional. More precisely, it's corresponding to the fact that we parameterize c by the real numbers. So that was an argument from yesterday. And I think Lion's question was, okay, but we can also parameterize by curves other things. Yeah. So what if you take a Peano curve in the plane? Why doesn't it show you that the plane is one-dimensional? So let me look at this example. So let gamma be a Peano curve. So this maps the interval to say the unit square onto. And if you look at it more carefully, it maps dyadic intervals to dyadic squares. The usual construction does. But this is important. We also have to look at how long the dyadic intervals are and how big the squares are. So it maps dyadic intervals of length 1 over 2 to the 2n, dyadic squares of size 1 over 2 to the n. So it's not the same exponent. The exponent here is twice bigger than this. And that's really the reason why the dimension will be twice bigger. So what is happening here? So now let x be a point in the square. And provided that I already know what the Peano curve is, I try to find x with precision n. So this is not more difficult than finding the Dyadic interval with precision 2n. So finding the gamma inverse x, this Dyadic interval, but not with precision n, but with precision 2n. And this is now a point in R. So this is bounded by 2n plus a constant. And when you divide by n and take an inf, what this really tells you is that the dimension of any point in the unit square is at most 2. And that's what you would expect because the square is a two-dimensional thing. So really the takeoff is that it's important to keep track of the scales. What do we define with precision what? And then we get the correct proof. So are there any questions about this?
Sure, it says something about how good space-filling curves can be at approximating things
Yeah.
point-wise. It's so interesting.
Okay, so maybe this is a good moment to introduce conditional things, where we can have two different scales.
My initial thought is you run into issues because the pyramid is like not injective, but I
Yeah,
think it's sort of
so
related.
whenever we do something like this, we need a nice correspondence between what scale is mapped to what scale. This cannot be just an arbitrary parameterization. So conditional complexities. And conditional dimensions. So this is something very similar like conditional expected value or conditional probabilities in probability theory. So first let's do the discrete version. We have two finite sequences. X and Y are sequences, finite sequences of zeros and ones. And then the conditional complexity is what you think. How difficult it is to describe X? If we already know why. So if, for example, they are equal, then we don't have to do anything, we just say they are equal. If there is really no relation between them, then it may happen that y doesn't have at all describing x. And the continuous version, if I have now not two finite sequences, but 2 points, so say x is in RD1, y is in RD2, they don't have to be in the same space. Then I can look at, sorry?
Okay, there is a request here to write bigger if you possibly can, but okay, because we can see. Okay, but yeah, you know that.
Yeah, for the size is the issue.
So would you like me to read something that I wrote?
No. What is written, I think we can, but try to.
I already write like twice bigger than I normally would. So this is not easy. Okay, so when I have two infinite sequences x and y, or 2 points RD1 and RD2, I can still look at the conditional expectation, but now I have to say with what precision. So let me put here an n and an m. And then this is what you would expect. So this is how difficult it is to find x with precision n, dyadic cube containing x of size 1/2 to the n, if we already know y with some other precision, m. So this is a type of thing that was happening in this piano curve example. And in the special case when an n equals to m, actually we use the notation, we just put the one index, k and x given y. And then you can speak about not only conditional complexities, but also about conditional dimension. So the dimension x given y is what you expect. Divide everything by n and take the limit, or lim sup. And you know the one to the Hausdorff for packing dimension of k and x given y divided by n. So this is one variant of conditional dimension, but it's not the only one. And sometimes we want to do something a little bit different. So another thing to do is when we want to understand x, provided that we know y, a different notion is what happens if we just use y as an oracle. So what is k and x? Now put y in the upper index. Y is now, I think of y is an oracle. So what does it mean that I think of y as an oracle? So y is now an infinite sequence of zeros and ones. So this really, how difficult it is to find x with precision n. Provided, and what people usually say is provided that we know every bit of y. So you want an oracle to be sequences of zeros and ones, and then you just take the first bit is this, the first 2 bits is this, the first 3 bits are that, which I personally don't find very useful. So let me write instead, provided that we know everything about y. Knowing its bits is not always the best thing to know. But in some sense, that's the only thing you need. So I have to decide what I mean by everything, because as always, I need to be careful about this. So everything here means computable things. So anything that can be calculated. Anything for which there is a computer program calculating it. From the bits of y. So from the binary expression. Y. So let me show you some examples. So most of the things you can calculate. That's not surprising, but there are some things you cannot calculate. So for example, you can ask, what is the densities of zeros? In y. So y is a sequence, 0, 0, 1, 1, 0, 1, 0, something. And I can just look at how many zeros I have in the first k bits and divide it by k. This is calculable. Of course, there is a very simple method of looking at how many zeros I have for a given k. But I will never be able to say what the limit of this is. So if you take k go to infinity and you ask what is the limit of the number of zeros up to k divided by k, there is no computer program that does it. Because by calculating something and saying that there's a computer program, I always mean it's a program that finishes in finite time and it outputs something. And if it finishes in finite time, it will never see all the digits of y. So yes, I can use information on every digit of y, but every information I use uses only finitely many digits of y. So that's somehow the key thing here. I can use everything about y, every fact that uses only finitely many bits of y. And once we have this, of course, we can define the dimension of x given y as an oracle. So this is, again, but depending on whether you want Hausdorff or packing dimension, lim for lim sub k and x y divided by n. So this was about conditional complexities. And something very closely related, let's look at joint complexities. So again, I have two finite sequences, x and y, finite sequences of zeros and ones. And now I'm really asking what is the complexity of x and y together. So this is really how difficult it is to find both of them, x and y. Which sounds like a trivial question, but it turns out that this is a very, very nice and very interesting question. So you will see, it's really sort of the heart of the matter of our proof. What can we say about joint distributions? So first of all, what does it mean? I'm asking how difficult it is to find x and y. When I speak about complexities, I don't want to have two sequences. I want to have one sequence, and that's how difficult it is to find it. So the first thing I have to do is encode x and y into one sequence. Not two, one sequence of zeros and ones. And how to do this is actually fun. You cannot just write down x and follow it by y.
One of the prime powers is
So if you write x, follow it by y, the issue is that you don't know where x ends and where y starts. So you don't know which pair this encodes. And that's an issue. So let's fix this issue. So the issue is that I don't know how long x is. So let's write in front how long x is in bits. But again, okay, now I know how long x is, but I don't know where this definition ends and where this definition starts. So seemingly I did nothing to improve this, but now let's do again something in front. Just write lots of zeros followed by a 1 to make sure that I know where this thing ends. So I can just look at, I start from 0, 0, 0, 0, find the first one. That's where the first thing ends. And the number of zeros I put here is how long is the second string. How long is, so this is first, 2, 3, 4. This is how long is 2. This is how long is 3, and this is 3, and this is 4. And now once you write down this string, you know what x and y is. Because first just you look at how many zeros you have here. Now you know how long x is, and now you know where x ends and where y starts. So this is a little bit longer sequence than just putting together x and y, but it's longer only by a logarithmic term. And this is a general principle, you never ever care about logarithmic terms. That's a good thing to keep in mind. So if x had length n, y had length m, then this is how long x is. That's a log n term. How long that one is, that's a log n term. So these are really negligible compared to the length of x. So what this argument shows is, so I have just proved this, that finding x and y is not more difficult than finding x and finding y. So complexity of x and y, this is bounded above by complexity of x plus complexity of y plus these logarithmic terms, log error. Which everybody would say, of course. I mean, it cannot be more difficult finding x and y than how difficult it is to find x plus how difficult it is to find y. So this is, of course. And another, of course, we can do better. It is also trivial to see that this, actually I shouldn't put here an n, but this log error, this is log of the length of x.
There's one.
Sorry?
One more.
There is one more n. Yes. So the joint distribution of joint complexity of x and y, this is also bounded from above by complexity of x plus complexity of y given x plus a log error. So this simply says that once I already wrote down x, there is really no reason to start from scratch. I can use every information that I already have. And so I already have x, and now find y. So this is also a triviality. When I write down this string, I have a computer program writing down this string. I do for x what I have to do, but then I can use a computer program to write down y, which already is allowed to use what x is. So this is also trivial. And that logarithmic error is really this logarithmic error in the front. So I promise you that there will be something exciting about this. So far there was nothing exciting about this. But now it comes. So this is a theorem which is called the symmetry of information. And this is actually probably the most exciting thing I have to tell you in these 4 lectures. It's in some sense the heart of the matter, the heart of every proof. It says that this is not just less or equal, it's equal. So kxy is equal to kx plus ky given x plus logarithmic error. So the upper estimate is trivial. As for the lower estimate, I think there is absolutely no reason why it should be true, except that it is. So this is my first remark. There is no reason why this is true. Other than the fact that there is a proof. Other than the fact that we can prove it. So it really says that if I want to find x and y, I can never ever do anything better than first finding x and then finding y. It doesn't matter how they depend on each other, what is the correlation between them. The trivial thing, just find one and then find the other, you can never ever beat this. So there is, I think there's really no reason why this is true. And my second remark is that this is really the heart of the matter of everything in complexities. So what I mean by this is if I look at every other part of every complexity proof, So you have seen already some yesterday. What was it? It's about the proof of symmetry of information. But that proof actually did. It was counting cubes. So we were looking at how many cubes we have of a given size. And from this, we deduced what the dimension of the set is. And as long as you do these kind of things, there is actually no reason to use complexity, because every such proof can be translated to a proof without using complexities. Maybe you have to think about it, and maybe you have to work hard, but really there is no important difference. Once you write down a complexity proof, you can always find a non-complexity proof. So this was the main reason why I told yesterday that when Jacob, this underexchange, showed me this proof, I didn't think that this was very interesting, because I thought, okay, whatever you can do using complexity methods, it's something you could anyhow do without complexity methods. But this fact, I don't have a geometric explanation for. So whenever a complexity proof uses symmetry of information, they all do, then I don't understand what this means in geometric measure theory. And this is what really makes everything, makes these methods to be very powerful. So that's why clever people like Don can improve known results in geometric measures, and that's why you can prove completely new, very difficult results in geometric measure theory. This is a new ingredient that we didn't have before. We don't have this in classical geometric measure theory. We don't understand what this means in classical geometric measure theory. But the proofs use this stupid fact, this shouldn't be true, and then everything becomes trivial. There are lots of things in geometric measure theory for which I don't know any trivial proof, and nobody does. But if you use symmetry of information, they become very trivial. So these are known facts that we knew before. I knew it all my life, but I always thought it was something very non-trivial, and now it turns out it is trivial. So Don asked me yesterday what I plan to speak about today, and I mentioned symmetry of information, and he asked me if I will prove it. And I said, of course, otherwise nobody would believe me. I can't prove everything in 4 lectures, but this is not optional. I have to show you the proof of the symmetry of information, otherwise you will never believe that it's true. I wouldn't. But before doing that, let's just use this as a black box. And I would like to show you some non-trivial effects of geometric measure theory, how to prove them trivially. So now we really go to geometric measure theory, which I always thought were non-trivial ones, and now they became trivial ones. So some applications. So the first one I would like to start with is about sections. So say I have a set in the plane, 2-dimensional plane, and I look at its vertical sections. So this means there is an x here, and Ex is the set of this line intersected with E. So the set of those y's such that x and y is in E. And of course it could be empty, it could be a very small set, but what this theorem says that it's usually not very large. So this is the claim that the host of dimension of Ex is what? It's 0 for almost every x if E had dimension less than 1. And it is the dimension of E at most. And it's the dimension of E minus 1 if it's at least 1. So this is again for almost every x. So I am not saying that this is a hard theorem, but it's not immediate. And I would like to show you that it's immediate. And in fact, I will prove a generalization of this. So moreover, it's actually not important that we intersect the set E with lines. You can intersect it with anything. So this is the theorem. If I have two sets in LD, any sets I like, and I look at the intersection of E with a shifted copy of F. So in the previous example, F was a line, but there is no reason why it should be a line. And I'm asking, what is the dimension of this for almost every Z? And the answer is that this was the maximum of the dimension of the product minus D and 0. So this is true again for almost every shift. So when F is a line, the dimension of a set multiplied by a line, that always increases the dimension by 1. So in the plane, this is dimension of E plus 1 minus 2. That's our dimension of E minus 1 for the lines. So this is the theorem. So this was known before. It's a theorem of Farponen. So he proved this when, under the assumption that E and F are arbitrary Borel sets. And of course, so this was some time ago, he didn't use complexity methods, so it was a proof using normal things. And then one of the three lots is the sun from the father and son pair. So Neil Lutz proved, find the complexity proof of this, and we don't need to assume that they are Borel sets. E and F are arbitrary. They don't even have to be measurable, and everything remains true. Which is something which very often happens when you use complexities. Actually, it's not easy to see what does it have to do with measurability, and often it has nothing to do with measurability. Okay, so I claim that the proof of this is very easy if we have symmetry of information. So let's see the proof. So the first step I just write down because it's a joke that David Price understands, and I don't know if it's in the audience or not, but the first thing to note is that if the intersection is empty, then we are fine. Because 0 is also equal to 0. So we can assume without loss of geometry that it's non-empty. And now so I will use, of course, the complexity characterization of dimension. So let A be what we call a house of oracle of the product set. So I think I should recall what I was saying about this yesterday. So we had this characterization for every set. And the house of dimension of E. This was the minimum for all oracles, the supremum for all x in E, the house of dimension of x using the oracle A. And there was an analog statement about backing dimension. So this minimum is attained with some oracles. And the oracles for which the minimum is obtained, these are the Hausdorff oracles. So this is any oracle A where we have equality. Where equality holds. And the same with packing. Something is called a packing oracle if you have equality in the packing version of this. So I just choose an oracle where I fix an oracle A where these two things are the same. That's what I mean, let A be a Hausdorff oracle of E plus F. So I write down that equation with the products at E plus F. And now the Hausdorff, okay, so let X be a point. Since the intersection is non-empty, I know that I have at least one point in the intersection. And this is really the same thing. Saying that x minus z, this is in E cross F. So the Hausdorff dimension E cross F, I know that this is at least, since this point is in the set, I know this oracle was something that lowered the dimension of everything below the dimension of the set. That's what the Hausdorff oracle does. That's exactly what it does. I may have some very complex points, but if I use the Hausdorff oracle, it lowers everything below the dimension of the set. So this will be below the dimension of the set. And let me continue here. It will be a long line, but it will be, proof is only one more line. So first of all, this is the same as, so the complexity of the pair x minus z, that's obviously the same as the complexity of the pair xz. Because if you know x and you know x minus z, there's an extremely simple computer program that calculates z. You just subtract one from the other. Also the other way around, if you know x and z, there is a terribly simple computer program that gives you that x minus z is. So calculating x and x minus z is not more difficult, it's not easier, it's the same difficulty as calculating x and z. And now I use symmetry of information. So this is the same as how difficult it is to calculate z, and then how difficult it is to calculate x given z. So before I wrote this down in a fixed scale, now I take lim-inf, and I just use that the lim-inf of a sum is at least the lim-inf of sum of the lim-infs. That's what this inequality says. And okay, so the last thing, so this term here and this term here, I have to look at them separately. The first one is just any point in the plane. I'm asking is what is its dimension. Z was any shift, and or not in the plane, in RD. And of course, we know that in RD, almost every point has dimension D. So this is equals to D, almost every Z. So this was again a theorem from yesterday. If you look at all those points of RD whose dimension is S minus epsilon, at most, this was an at most S minus epsilon dimensional set. So those points which doesn't have full dimension, these you can write as a Cantor union of sets that don't have full dimension. And then, of course, it's a null set. So for almost every point has full dimension. Now, what about the other term? So this term here is larger than this. So in this one, the first one I can use, and you look at it in a fixed scale, you can use the first n bits of z. Here you can, when you put z in an oracle, you know everything about z. So of course, if you know everything about z, that won't be more difficult to calculate. If you know everything about z, it won't be more difficult to calculate x than only if you know some information about z. So everything I did was really trivial so far. And I have to add something to this line. So this is so far true for every point in the intersection. But, okay, this is stupid. I did write on another blackboard. I didn't finish the one line. So now we can choose any, this is true for any point in the intersection, so choose x from the intersection such that this thing here, this last term, is larger or equal than what it should be minus epsilon. So this is using that the Hausdorff oracle lowers everything below the dimension, but we know that nothing can really lower everything to this minus epsilon, because there was an infimum. So the Hausdorff oracle does the best thing possible. If I want to improve this by an epsilon, I can't. So what does it mean? I will always have some point whose dimension is bigger than this. So for every epsilon, since I cannot lower the dimension of every point below this, I can find a point which is not below it. And this is true for every oracle. In particular, it's true for the oracle, which is the pair of A and Z. And now we are done. So if you just look at this line, I prove that this one is larger or equal than D plus this for every epsilon. And that's what we wanted. So dimension D plus F is larger or equal than D plus dimension of the section minus epsilon. And this is true now for every epsilon and for almost every sigma. So that's the whole proof, really. So are there any questions? I mean, nothing happened in this proof. Maybe it's surprising at the first time, but I will show you like 4 more proofs of this type, and then it's just your basic part of your toolbox that you always do, and you will say that there is nothing to prove here, this is trivial. You just look at it and you say, of course. So are there any questions? So if not, then let me show you another thing of the same type. This will be again an of course proof using symmetry of information. But this is again did I say it? Yes, I said that it was by nil roots. This is another theorem by nil roots. Which is again something we knew before for Borel sets. The proof was really highly non-trivial. And now it turns out it's true without the assumption of Borel. You don't care whether the sets are Borel or not, and the proof is trivial. So the statement is, if you have E and F are arbitrary, and this will be a long line, the packing dimension of E plus the packing dimension of F is at least packing dimension of the product. This is at least packing dimension of E plus the Hausdorff dimension of F. this is at least the household dimension of the product, and this is at least the sum of the household dimensions. So when I say this is a non-trivial fact in geometric measures for Borel sets, so the proof of this type of things, that the product of two sets has dimension between these two things, it uses Frost-Swan's lemma, it uses like energy integrals, it uses capacity, and now there will be a one-line proof using symmetry of information. So maybe there are better proofs, but I don't know any simple proof. I didn't know any simple proof before. And I thought all my life that this was not a trivial fact. And it turns out it is a trivial fact. So once you have some experience working with these things, you see something like this and you say, of course. So why it is an of course? Proof. So this is really of course, because if I have two sequences, then the lim sup of the first one plus the lim sup of the second is at least the lim sup of the sum. It is at least the lim sup of the first plus the lim inf of the second. It is at least the sum of the lim inf of the sum, and this is at least the sum of the lim inf. So just for fun, let me write this down. Lim sup xn plus lim sup yn. This is larger than lim sup xn plus yn. It's larger than lim sup xn plus lim sup plus lim inf yn. It's larger than lim inf of the sum. And that's larger than the sum of the lim inf. And that's something that you probably knew when you're a baby, and if you knew this when you were a baby, then you also knew this. So why? So now if I write the same thing with complexities, so what this means, the packing dimension of x plus the packing dimension of y. So this is a lim sup, this is a lim sup. This is at least, sorry, I understood y. Use symmetry of information. Packing dimension of x plus packing dimension of y given x. So on a fixed scale, by symmetry of information, this would be the complexity of the joint distribution, joints and complexity of x and y together. And then when you take lim sup, this will be now larger than the lim sup of x and y. And this will be, by exactly the same argument, it will be larger than the packing dimension of xn plus the household dimension. Packing dimension of x plus the household dimension of y given x. And that's larger than the household dimension of x comma y. And that's larger than the household dimension of x plus the household dimension of y. So nothing happened so far. On a fixed scale, they would be equal. And then you let n goes to infinity and put lim sup and lim inf in these inequalities. This is exactly what you get. So in a fixed scale, complexity of x plus complexity of y is the complexity of x and y. That's what symmetry of information is. And the rest is just this triviality. What happens when we take look at it on final scales and let n go to infinity.
So how does like the last inequality work? Like how do you go from y given x to y?
I forgot. Sorry, it should be y given x, and this is also y given x.
So you can upper bound that by y.
everywhere y should be y given x. Okay, so we know this with points, and now we want to write them the same with sets. So let's look at, I have to look at all these, where is it? All these inequalities separately, but basically I will just repeat the same argument 4 times. It's very small differences. And I told you, if you have seen this 5 times, you will say always that this isn't of course. So you will see it 5 times. You already have seen it once with the sections, and I will show you the same argument 4 more times. So let's look at the first one. Why is it true that the packing dimension of E plus the packing dimension of F is at least the packing dimension of the product? So this is how the proof starts. Let A be now a packing oracle. Of these 3 sets. So packing oracle of E, F, and E cross F. So of course you have a packing oracle of each, and then you can take the union of these 3 oracles. It's still an oracle, and it's now good for all 3 of them. Actually, you don't need that it's a packing oracle, all 3 of them, but this way I have to remember, don't have to remember which one of these I need for the proof. So easiest is just to say, take an oracle which is good for everything, and let x be in E, y be in F, and now try to find the lower estimate for the sum of these packing dimensions. So I know that this oracle lowered the complexity of these below these. So this is at most packing dimension of x using the oracle plus packing dimension of y given x using the oracle. And now let's put this x into an upper index. Do I need that? No, I already wrote this. This is what I need. Okay, I have to explain this correctly. I'm doing now, I think it's slightly incorrect. No, okay. Packing dimension of. It is slightly incorrect. I need it in the upper index.
This one.
So what I want, so let this choose this such that the packing dimension, this is larger than the packing dimension of E minus epsilon. And I also want the second term to be larger than the AX. Okay, it is correct. Maybe. Packing dimension of AX Y should be larger than packing dimension of F minus epsilon. So this I can always do. I can find an X from E, I can find a Y from Y whose divergence is not lowered too much. And now I can simply say that this is larger or equal than this plus putting X in the upper index. course, if I can use every information about x, things become easier than if I can just use some information about x. And now we are done. So now it is correct.
There's like a minus epsilon here, because it's taking
The
points.
minus epsilon is coming now. This minus
sorry,
epsilon plus packing dimension of f minus epsilon. So this is true for every epsilon.
Okay, the first line is wrong, then I think, right?
Which
One of
line
these
is
should be
wrong?
the product.
I'm sorry?
The first one should be the product, right? Not the sum, the packing dimension.
That should be a product.
That's always true.
Yeah,
Because-
I mean, that's what I'm saying. So the first one
Okay.
should be
Maybe
the
I
x
write
right?
it. Write the term between them. I hope it will be clear. Did I do something? Yes, so the product.
I think you're missing a line here where it's more than.
So this is
than
more
p
than
of
the
x comma y. Right?
X, yes, exactly. Which is more than this.
No, it's the other way around, right?
Other way
If
around?
you use the inequality above, right, dim PA x plus dim PA y given x is more than dim PA of x comma y, right? So then at the bottom, you have
I
the product.
messed this up, it seems. So,
Right or not? And isn't all this says that like if you also have the information of x, it's no worse than if you had no information from x, and the definition should be the same.
I think at
By
the,
mutual information.
the second line, you want to use symmetry of information to drag them together to get E cross F.
incorrect.
Yes, exactly. The last one's yeah.
This
correct.
is equal to this and Y. So let me. So you want. Where's the? Sorry. So I'll write
I
it.
think I want the joint one to be larger than this minus epsilon.
Yes.
That is correct.
There we go.
Yeah. The joint one is larger than dimension of the product
Yeah.
minus epsilon.
Yes.
Okay. Maybe I'll add it over
No,
here.
yeah.
The beginning was it should be b plus f. And that one is equal. You were right before. It was
Yes, and then this is, yeah, and then this is, dim P E plus dim P F. Yeah, because that always, okay.
Okay, so sorry about this. But are there any questions now? I messed it up, but it's still.
There is a question here.
Yes?
Come here. I think if you come. Just a second.
I'm sorry?
Wait, where do I?
Can you hear Marianna?
Hello?
I hear Giovanni.
Okay, come here.
Hello? Do you hear now?
Yes?
Okay. So is A both the packing oracle and the house dwarf oracle here? Is that?
Everything in this line should be packing. Packing.
Oh, sorry. That is still packing. My bad.
And A is also a packing oracle for everything. So what this says that, so the first inequality is true, dim PE plus dim PF is larger than this because the packing oracle is something that lowers the dimension of everything below. So this will be true even without y given x.
Yeah,
It will be just true with y. When I put y given x, it makes it even smaller. The second line is what I had there already. So it's the lim sup plus lim sup is larger than some of the lim sups, and we have symmetry of information. And this is true if we choose x and y such that this dimension is not lowered too much. That's the whole argument. So now let's see if I can do the other inequalities correctly. I will cheat, I will look at my notes, and I hope it is correct. It was correct when I wrote this down an hour ago. So this was the first inequality. Now let's do the second, and I really just want to copy the same thing. That is the, yeah, so this is what I'm proving now.
Sorry, Marianna, can I ask a question?
Yes? Sorry,
So,
I didn't answer your question.
Did you use the symmetry of information so far?
Yes, when I wrote this, I used symmetry of information.
Okay, so it's an equality,
Here
right?
I am using that the lim sup of a sum is at least the sum of the lim sups, and I'm also using the complexity of this plus the complexity of this is the complexity of the sum.
Okay,
So I'm using that the complexity of the joint distribution is the sum of these two complexities on a fixed scale, and that's symmetry of information, and then I take lim sup.
Okay, so let me,
The proof of this
right.
is
In
the
the
theory
symmetry of information,
from nursery school. This is symmetry of information, and this is just putting things together.
okay. So can I ask a question? In the symmetry of information, it's an equality, but one of which can be written as two inequalities, one of which is obvious, one would say, right?
I hope all of them are obvious.
No, it's not an symmetry of information. One.
Yeah. So yes, but here I'm pretty sure I'm using the non-trivial direction.
Okay, yeah, that was the question. Okay, fine. There, yes.
Not always, but not always. Sorry, not always, but
Okay, fine. Sorry.
the non-trivial ones I am using the trivial direction of symmetry of information.
You're about to use the non-trivial one.
Yeah, as Don is saying, now I am about to use the non-trivial one for the second inequality. So in the first one, I started with the left-hand side. Again, I start with the left-hand side of the inequality, so that's what. I'm looking at the packing dimension of the product. I'm copying this proof. Now this is larger than something. So this is larger than the packing dimension of x and y. Now I use symmetry of information. So this is larger than the packing dimension of x plus, now it's the Hausdorff dimension of x given y. So for this, what I need, so before E was an oracle, packing oracle for E and F and E cross F. Now I have to use a different oracle. I have to use an oracle which is packing for E cross F, packing for E, and Hausdorff for F. So I choose a packing oracle for this, a packing oracle for this, a Hausdorff oracle for this, and take their union. That's my A. And I try to copy this proof with that A. So did I make any mistakes so far?
I think it's y given x.
Y given x, yeah, that was just a typo. Okay, so this is larger than plus, but if I use everything about x, ax, y, and I can tell you how I choose and how I choose x and how I choose y. I choose x such that this term here is larger than the packing dimension of E minus epsilon. And then I choose y such that this term here is larger than the Hausdorff dimension of F minus epsilon. So, except for the last step, everything was true for every x and y. And now this is how I choose x and y. Yes?
So the idea, if I understand this, like the oracle's already sort of almost maximal.
Yeah,
so
exactly, yeah.
Always it's going to be independent of the other point you choose, sort of like up to an epsilon. It's using
Yes,
like an, okay,
yeah.
that's interesting. So it's like how do you go
Yeah,
from y
that's,
to
that's,
x
that's
to y?
the,
But
that's the
yeah.
idea. So let me do this 2 more times. I'm running out of blackboards. I think I have to delete symmetry of information, but hopefully you all remember right now. Okay, so for the third one, I want a lower estimate for dim PE plus dim HF. So now A will be an oracle which is packing for E, Hausdorff for F, Hausdorff for the product. And I can say that this is larger than dim P AX plus dim H A Y given X, which is larger than if I put this in the oracle. Seems I don't even have to put it in. Okay. I'm copying this. I guess I have to put it in the oracle. So I want to use this thing. I want to say that this is larger than the Hausdorff dimension, even A. I don't have to put it in the oracle for this one. All I need is to choose xy such that, so choose xy such that this is larger than the Hausdorff dimension of the product minus epsilon, and I am done. So you don't always have to put it in the oracle. So that was number 3. Number 4, too many blackboards now, so what I'm doing. That one, the last thing for the year. So dimension E cross F Hausdorff dimension is larger than Hausdorff dimension of x, y, which is larger than Hausdorff dimension of x plus Hausdorff dimension y given x. Now I put it into the oracle, I guess. Now for which x and y I apply this, so I choose x such that this is the dimension of E minus epsilon, and then I choose y such that this is at least the Hausdorff dimension of F minus epsilon. And that's really now end of the 5th book today. So all of them are pretty much the same, and all of them are pretty much nothing. You just have to be careful not to make stupid typos or stupid mistakes. Questions?
Questions here?
Anywhere.
So is this the end of the lecture?
No. It's just the end of this.
Sorry.
So now, what is the time? I hope I have, I have a lot more time. So now my next, let me give you a homework exercise. It will be slightly more difficult than yesterday, but Hopefully some people can do it. This is the homework. So we know that the dimension of E, I just write one of these inequalities now. This is larger or equal than the packing household dimension of the product minus the packing dimension. This is true for every F. So I can put here supremum of this for every F. This is always true, but is it equal? That's the whole question. Okay, is it true that for every E you can find an F such that equality holds? And you can ask exactly the same question with all the other inequalities, but I don't want to write down the same proof 4 times. So one of them is enough for each other. Okay, so I hope you all agree now that symmetry of information is important, and there is no way to get out of it. I have to prove it. So let me start the proof. It won't be a long proof. It will be actually a surprisingly simple proof. But I think I need to recall a few things from yesterday for this that you may not remember, or maybe I didn't explain this very well. So recall, when I stick our definitions, it is okay to have an upper bound. Okay, to speak about sequences. So I will make this a little bit more precise today. It is okay to speak about kx is bounded from above by something, but it was not okay to speak about kx is bounded from below by something. So what did I really mean by this? So now there will be some formal definitions explaining what did I mean by this. So this is some definition from computer science. We say A is a set of finite sequences. A is not finite, but the sequences are finite. A is a set of finite sequences of zeros and ones. And then A is called, I hope that it is called like this, right? Enumerable. If there is some machine, so if it is an output, if there is some program that lists the elements of A, but unlike before when programs were finite, this is not a program that you start it running and it runs forever. A may be an infinite set, but what it does, it splits out the elements of A. Then we say that A is enumerable, otherwise it's not. And now the fact is that if I look at those x's, kx is bounded from above by something, this is yes, it is enumerable, but the set of those x's which are larger than C, this is a no. So this is what I was trying to explain last time a little bit. And I don't really care about the fact that this is no, but I care about the fact that this is yes. So why? So we had a wrong proof yesterday, and now that wrong proof will become a correct proof. So the wrong proof was run every program of length at most C. And this was a wrong proof because these programs may never stop, and then you cannot just run every program of length less than C and see what their outputs are. But now it is correct because programs are allowed to run infinitely many steps. You still just cannot run one program and then you run the next and then you run the next. That would not work, but you could say run each of them, look at their first 100 steps, then run them again and look at their first 1 million steps. Run them longer and longer and longer, and now what will happen? They will write down the set A. Because each program, if you run it longer and longer and longer, then eventually you run the program. So that's the proof of this fact. And now it's easy to see, it's really an easy fact, that if A is enumerable, and X is in A, and it's a sequence of lengths n, then the complexity of X is at most what? So if I want to find X with X, then all I have to do is run this program that writes A. It writes me every element of A which has this length, and I just need to specify which one I am looking for. So this will be at most the log of the number of those Y's in A whose length is n. So I just want to say that I'm looking for the case one. Among all of those which has length n, I'm looking for the case one. A is enumerable, so there is a program that lists all of them. And okay, I'm not allowed to now use infinite programs, but I just say, let's stop after you found the case one. And that shows that really the only thing that I have to write down is what k is. Everything else is a constant in this sentence. So this is because we just need to specify specify where X is in the output. And we can just do this by saying that it's the case one among those that has length n. And once you found the case one, you just stop the program. So the length of this sentence is like log k. Upper bound for the log k is how many you have of length n. So it's log of how many you have length n. So that's why this is always true. And this is really the only thing you need to know to prove symmetry of information. The rest will be a very trivial counting argument. And I still have 8 minutes, I think, so I can show you this trivial counting argument. So really there is nothing, this is, I think, is super surprising. It's a very powerful, impossible statement, but its proof is very simple. It's a counting argument plus this easy observation. So now I will prove symmetry of information. Proof of symmetry of information. So given X and Y, we want to show that something is true. So let A be the set of those U and V. Everything here is a finite sequence of zeros and ones. Let's look at those sequences whose joint complexity is bounded by the joint complexity of X and Y. So how large is this set? So I'm looking at a set whose complexity is bounded by something. This is my enumerable set. X and Y are fixed. I'm looking at everything which is bounded by this. But how many programs I have of this length? At most 2 to the k xy. So trivially, the side of A is bounded by 2 to k xy. That's a trivial fact. Another trivial fact is that X and Y is in A. So that was the first easy step. The second easy step, now let V be the set of those V's, that XV is in A. Okay, so the easy observations, y is in B, xy is in A, and also the complexity of y given x, this is bounded by log B. Log B? Yes. So this was an enumerable set, and I know that if I want y, I just have to say which element of B it is. So its complexity cannot be bigger than the log of the size of the set. So that's this type of thing. And the next one is the trivial counting argument. So it basically just says, this is my set A. It has this many points. That means I cannot have too many vertical sections which are very large. The number of vertical sections times how large they are is bounded by the size of my set. So let's write this down. There can be at most size of A divided by size of B many U such that the set of B's, U and B is in A, is larger than the size of B. So there can be only this many vertical sections which have size larger than B. There can be at most A over B many vertical sections larger than B. If altogether I have only A many points. And we are done. So this shows that K of X, since X is on a large section, X was in this set, so K of X is bounded than log of how many sections I have, and we are done. So I have an upper estimate for K of X, which is log of A over B. I have an upper estimate for Ky given X, which is log B, so it's neater. Let me write this down. I just copy the same formula. So K of X is bounded by log A minus log B. K of Y given X is bounded by log B. And when you sum these up, K of X plus K Y given X bounded by log A, we have an upper bound for A, that's Kx given Y, X and Y. So this is the non-zero direction, the symmetry of information. I don't have to prove the other direction. So I ignored log factors everywhere in this argument, but that's okay. All the time there, in everything I write down, there is a logarithmic error. So that's really the proof. This is the whole proof. You cannot have too many big vertical sections if your set is not too big. That's what symmetry of information really does. Questions?
It's like Chebyshev's inequality.
I call it Markov, but yes.
Yeah.
So it is really a very easy proof of a statement that shouldn't be true. And since this shouldn't be true statement is true, we can do lots of interesting things in geometric measure theory that we couldn't do without. So next time I will show you things that we really couldn't do without. Not just that we have a new proof of something we knew before, but we have new results. And this will be deeper than what was happening today. This will be non-trivial proofs. Everything today, I believe, was a trivial proof. My time is up, am I right?
Yeah, you have 5 minutes more if you need.
I have 5 minutes more, so I didn't know.
Well,
so I would like to. Okay, I would like to say something more. Like a preview of one of the things I will be explaining next time. And this is, I mean, every proof I show you today, they were working for arbitrary sets. So it didn't matter whether sets are Borel or not. So this is an important observation. So remark is that all the proofs so far work for arbitrary sets. And this is most surprising. I mean, I didn't expect this, but it's also worrisome because it cannot be true. It's not true that every interesting statement in geometric measure theory is true without some assumptions on the sets being Borel or analytic over. So this is worrisome because it somehow says that using complexity methods, we cannot prove anything unless it's a statement that happens to be true for arbitrary sets for some mysterious reason. And there are lots of statements in geometric measure theory where, for example, using continuum hypothesis, you can easily construct cheating counterexamples when the statement is not true. So this looks like a serious issue. We want to prove also statements which are not true for arbitrary sets, and then what can we do? So this is when you need somebody as clever as Don. I don't know if this was your thing or you did it together with some of the others. But so this is something I will do next time. I will define something which is called optimal Hausdorff or packing oracle. So it will be a Hausdorff oracle with additional properties. And there will be some proofs that will, so far it didn't matter, but now there will be some deeper proof that will use these additional properties. So it won't be enough that an oracle is just Hausdorff or packing oracle. We want to say something more. And it won't be a complicated definition, what I mean by Hausdorff oracle, but there are two facts about this. Every analytic set will have optimal oracles. So that's somehow why everything is fine. So in geometric measures, we usually prove statements about analytic sets. Now we will have some proofs that works for every set that as an optimal oracle, then these proofs will be working for analytic set. But now you can ask, can we always find, not only for analytic sets, but for every set, can we always find optimal oracles? And the answer will be, it's here, it's independent of ZFC. So under continuum hypothesis, no, which is very good news. So under continuum hypothesis, it will be easy to construct a cheating counterexamples. Usually it is. Under continuum hypothesis, no. And under some other set theoretic assumptions, which is AD, axiomatic determinacy, which is something I definitely won't speak about. So there is some axioms under which the answer is yes. So it's independent of ZFC, and yes, if you assume continuum hypothesis, there are many results in geometric measures for which you can construct a cheating counterexample. But that's why you can construct sets which don't have optimal oracles. And really the main conjecture this is something we sort of believe to be true, is that every statement in geometric measures remains true. I know this is a bold statement, but every statement in geometric measure theory remains true if we replace the assumption that the set is analytic by having an optimal oracle. So it somehow seems that this is the only thing that matters. So whenever you try to write something, try to prove something using complexities that we already know it was true for analytic sets, if you are a very good mathematician, you can find the proof, and the proof we use optimal oracles. If it's a deep theorem. If it's a less deep theorem, you don't need. Like the theorems today, they didn't need optimal oracles. So I will speak about optimal oracles next time, and I will, maybe next, I don't know which lecture, but I have 2 more lectures. I will also show you some of the proofs where you need them. So is this your definition? Yeah, it's Don's definition. So I will write down the definition tomorrow.
Okay.
So this is now at the end of my talk, I think.
Okay. So let me ask harder questions.
Mm-hmm. So that is your question?
No, I'm asking the people.
You're asking your audience, yes, sorry.
There are questions. Actually, I have one, if there is no. So let me put this way, maybe a bit naive. So in these proofs you gave, coverings completely disappeared in favor of, if you like, a formula for the Hausdorff dimension or packing dimension based on complexity. Now, there are other proofs where you don't use covering because you replace them, say, with...
when I use complexities, I always replace them.
No, wait.
Coverings will never reappear again. I think this is close to being true. But it is a covering argument. So the proof of the symmetry of information was a covering argument, and I am not
okay.
that. So the proof of the point to set principle was a covering argument, and that's the formula for the dimension. That's something I use all the time. So yes, I use it. It's just hidden.
No, but it's fine. The question
Covering
is
in the point to set principle, symmetry of information is something else, and every proof combines these two.
So I have this question. So can you prove in the same way the statement that usually people prove using potential theory like projections? I mean, the results of...
Projection theorem is part of these things that we can prove, Don can prove, and that some other people can prove if the set has a oracle. Marsan projection theorem remains true.
Okay. Yeah.
So I plan to say something about Furstenberg and Cocker problem. I plan to say something about Marsan projection theorem. I plan to say something about Falconer's sunset problem. And I know for sure that this would take more than 2 lectures. So I will see what I can fit into 2 lectures. But these are the type of theorems where you can do this.
Okay. I'm asking here, other questions? Okay, if not, let's thank Marianna again.